in his background. Uh, where we are as far as formal replications are concerned is that Martin and his students did a so-called replication a year and a half ago. Hal took the stuff to them and set it up with them and all that. We had the calibration issue. So they were seeing stuff that looked like what we were seeing after not seeing anything a year earlier. But it's alleged that it was significantly smaller than what we were looking at. It turns out a factor of 4 of that was the calibration miscalculation. Okay, so what they were seeing, we have heard that Martin allowed us how they saw thrust type signature events of several hundred nanonewtons, and that would be consistent with what we were looking at the time. But they reported a null result. They took our device. We had provided them with a vibration isolation yoke that Hal talked about this morning. As soon as she left, they took the yoke out and bolted the thing directly onto their balance, and not surprisingly, they saw vibrational effects. They were convinced that that was what was the cause of all of the signals. When Martin visited us a year ago, at the end of August, this past August, a year ago, he allowed us how this was what they were going to report out to the public. We got out our Polytech vibrometer that you heard about this morning and showed him that the device on our balance, which was producing thrust, which we had shown him, was not producing vibrational artifacts that would account for them, that indeed the balance was isolated from vibration in the Faraday cage. And since the Faraday cage, aside from the energy input, is a closed system, momentum conservation says you can't produce a quasi-stationary force on the balance without some vibrational thing getting to the balance. Okay, so that's where things have stood for the past year. We've been primarily interested in increasing thrust because that's what everybody wanted. As I told you this morning, David Brin made the comment at Huntsville last year that this calibration and vibration stuff was all sort of interesting, but what about more thrust? And that's what we've been focused on.
What is the order of magnitude of your thrust signal, Jim? Just order of magnitude?
The thrust, let me tell you in a nutshell what we are looking at now. And I will explain how we got it, and then I will let Paul and Michelle and Chip Atkins talk to you about how all of that came about and so forth. I'll show you how the things are built. The thrust signatures that we're seeing now on our thrust balance are quasi-stationary. We're looking at very high Q events which produce thrust impulses, and our balance is a low-pass filter for such things, such signals. But even with it being a low-pass filter, we're seeing tens to hundreds of micronewtons of thrust in the signals that we see. Okay.
Thank you.
If we can, and literally you can see these things under sufficient power move on the balance. You can literally see the forces moving the thing back and forth and so forth. Okay, and Michelle's going to show you some pictures, some movies of that with motion enhancement and without motion enhancement. The most extreme of these things is displacements of the device, which is 125 grams by between a half a millimeter and a millimeter on the hardware that they're mounted on, which takes place in perhaps 100 milliseconds. And if you do a back of the envelope calculation, you'll figure out that that's producing millinewtons, if not more, of thrust. So these, and the question is, how did that happen? Because we're running about the same power as we've been running all the way along, all the way from the stuff that was producing a few hundred nanonewtons on up. And the answer is very simply, I'm going to hijack the screen and I'll show you how we do it. Okay. Hal's already alluded to this. Okay, there's my screen. Let me get on here and get to the right folder. Okay. All right. We got some movies, but we got some pictures here. Okay. Basically, the development that took place in early June was, you remember that Hal told you about the sledge mount setup, the two dowels, the device sitting on the dowels, free to slide back and forth with stops to limit the motion and all that. Uh, and that when that mount was used, that the high frequency vibration that made it to the Faraday cage was significantly reduced from just mounting it on an L bracket. Okay, you've seen the L bracket and rubber pads. Okay, what we were running at the end of this was so-called Belleville washers. Okay, this was our way of treating the heat problem. This is a reaction mass with Belleville washers glued together, which is pretty klutzy, to tell you the truth. John wasn't in the machine shop, so all of this was done with hand tools. This is another view of the same device. You'll notice over here that there's a flange on this reaction mass. Basically, what happened was in early June, I looked at that and I looked at the flange, which was there because Paul and Michelle were talking about a design that involved some really big, heavy, clunky Belleville washers. I looked at it and I said, gee, to myself, gee, maybe you can stick the dowels through that and get rid of all of this stuff with L brackets and washers and stuff like that bolted to the back of the reaction mass. Okay, and that is in fact exactly what we did. Okay, let me go back. Where the hell is back? Here's back. Okay. Um, Basically, what I did was I said to myself, haha, if we make a reaction mass like this, okay, which is just a 7/8 diameter cylindrical reaction mass, nothing bolted to the back or anything like that, and you move the flange that you saw in the other case up to the interface with the PZT stack here, okay, and you put 3 holes through it like so, those 3 holes, what you can do is you can line that with Teflon and build an aluminum frame around it, okay, and the aluminum frame around it, let me get back here, will give you this as a proof of concept device. Okay, you'll notice that there are lots of washers under the bolts that hold the stack onto the reaction mass and so on. But here's that flange sitting on a 3/32 steel dowel. There's another one down here and the third one in the background. Okay, little rubber O-rings stacked as stops for the thing to move, but other than that, there's no pressure on the flange, so forth. And we ran that, and lo and behold, it worked. It started producing stuff in the tens of micronewtons range. Uh, okay, the duh moment involved was, gee, let's just move the mounting system, which in effect tries to decouple the high frequency vibrations from the rest of the apparatus. The idea here is that the high frequency vibrations are the ones that produce the Mach effect. And when you have them hooked up to anything else that tends to damp those high frequency vibrations, the Mach effect goes down the toilet. So the rubber pads and all of the Belleville, the washer arrangements and all that were less than ideal because they all tended to attenuate high frequency vibrations. This system in principle should not attenuate high frequency vibrations. The only forces that would do that are frictional forces, and that's why those things were lined with Teflon tubes. Okay, and it was clear that this was a preferable way to go. There was a second duh moment in this, and the second duh moment was Jose's. If Jose wants to tell you about it, I'm perfectly happy to have him over and take over and tell you about it. If not, I will Continue, Jose. Ah, Jose's not interested. Jose's not talking while the flavor lasts. Okay, here we go. Uh, the second duh moment was, gee, uh, it's really nice, you know, to have Teflon and all that, but Teflon on steel has a coefficient of friction of 0.01, which is a lot smaller than the coefficient of friction of brass on steel, and so on. But maybe what we can do is make a phase 3 proposal to NIAC on grounds of introducing linear ball bushings instead of Teflon lined tubes. Because if we have linear ball bushings in there, given the high frequency vibrational environment, you don't have any stiction or static friction involved because of the vibration, which makes these things, if you have linear ball bushings sitting on those rods, essentially frictionless, which means that you are in effect, if you don't have anything pressing on the ears that hold the ball bushings, uh, makes the thing essentially the equivalent of doing this in free space. Okay, so you've seen the proof of concept. Linear ball bushings, which look like this, okay, that's a linear ball bushing. Paul and Chip can tell you about how we got to these. They're 2 millimeter ID and 4 millimeter OD by 5 millimeters length, okay? And those things get stuck in the ears of, let's see, I'm not sure if I've got the sequence of this. Yeah, let me go on here. Those things get pressed into the ears of a reaction mass of the same sort that you saw with the proof of concept thing, only the flange has been machined away except in the area of the ears, and the bushings are, in this case, pressed in flush with the reaction mass. The ones that are being built now, the flange that holds the ball bushings is reduced in thickness so that the ball bushings stick out about 30 thousandths on either side, and they will ultimately be used to center some helical springs that are used with them. That sits on this thing here, which is a what I call a shoe plate, the shoe being this red piece of plastic attached to the bottom of the plate. That gets attached to whatever hardware you're sitting it on. Ultimately, it gets attached to something that's on the vibration isolation yoke, because that's still part of the apparatus. And then you have another plate here, which simply goes over the other end of these rods, and you put spacers along between the screws. On the screws that hold the plates together, there are 4 screws in the 4 corners, and those 4 screws with the spacers determine, this is the device which is presently in the tank on hardware being put together. This is it sitting on that shoe plate on the rods, okay? And you can see the ball bushings there and so on, okay? You put on that other plate like so, and these spacers and washers determine, in this case, it has helical springs on it instead of the arched springs that Hal showed you this morning. You can see that they don't hang properly on the ball bushings because this one's sitting on the thing. As long as there's no pressure exerted by the springs when it's sitting there like this on the ears, there's no trouble. It turns out that if you apply pressure to the ears, you know, of sufficient, of the sort that you would apply by compressing the springs significantly and all that, it screws up the behavior of the device and the effect goes away. Okay, but as long as the springs don't apply any pressure on there, I'll show you a movie of what happens, in fact, with this device in a moment. Okay, so this is the way it's held together. It's basically the device hangs. You turn this counterclockwise 60 degrees or 90 degrees, and the 2 rods, this rod and the rod down at the bottom here, okay, are the ones from which it's suspended, and this is the one that guides the thing down there. Okay, now, okay, all right, we're finished with that. Okay, proof of concept. Okay, question is, how do I, this is how I do that. Okay. Okay, I'm not going to show you the thermal stuff. I'll show you that this morning. Okay. Let me show you a movie of how that thing works on the device that we're talking about. This is PI. I'm showing you this not because it shows you a really spectacular run. You can actually see the end result of the runs in these two picoscope traces that are in front of you now. The one on the right is the one run at a little bit higher power than the one on the left. And you can see this thrust effect here. That's peak. This is the peak to peak. This is the full scale 40 micronewton scale. So you're talking about half a dozen micronewtons or thereabouts, okay, for the event. But what this does very nicely is it shows you very clearly that that thrust event only occurs when you have the second harmonic come into existence and with the right phase. I'm going to show you the movie now. Let's see what this comes up as. Okay. Do you want me to expand this? Yeah, I may as well. Okay, here we go. All right. Now, the FFT, there it comes on, second harmonic, there's your signal, and then the second harmonic goes away. Okay, let me stop this and run it back through that event again without all of the lead in. Okay. Watch the second harmonic down here. There it goes. Now it's gone. Okay. If you look at the waveforms over here, Hal's got the waveforms and voltage scales set for much higher power operation. So there's not too much to see, I'm afraid. But if you look very carefully at the waveforms over there, actually I can move this slowly through them. Okay, you can see the red trace in the waveforms. You have second harmonic presence, and there's not much second harmonic presence in, well, there's a little bit in the blue trace, which is the voltage and so on. Okay, and then it goes away, and all you see is the voltage trace. Okay, now what you're going to see when I, in about 2 minutes or less, yield this over to Paul and Chip and Michelle, is you're going to see stuff that's at least as impressive as that. What you'll see is actually a movie or two, I hope. Michelle has got the movie or two going. Okay, let's see, let me collapse this. Okay, and get rid of this. Okay. What they are going to do is they're going to tell you about how we have gotten from, to me, just fooling around with the PI Ceramics makes a disc that is similar to, but not exactly like, the Steiner Martin's 111 discs. She's unshared my screen. Yes. So you're seeing my mug as I say this. Okay. Yes. All right. PI Ceramics makes material that has a higher stiffness, mechanical stiffness, and a lower dielectric constant slightly than the Steiner Martin's 111. The Steiner Martin's 111 produces really very, very nice results. Okay. We tried the American piezo ceramics materials, which is a little bit worse in stiffness and a little bit higher dielectric constant, and that doesn't work very well at all. Okay, so this was a test of other materials, and if we get done early enough, Hal can run the device, which is in there. At one point, VRMS on the signal generator is the way in which we adjust the amplitude of the voltage across the device. The first one, which showed a little bit of a wiggle, was at VRMS equal 0.5 volts. The one that I showed you the movie of is at VRMS 1.0 volts, and she's going to do VRMS of 1.2 volts if we get to a real life demonstration of this. But before you see that, Paul and Chip and Michelle are going to take over, and they're going to tell you all about how we got from early June with Jose's insight that linear ball bushings were the right thing to do to where we are now. But where we are now, in a nutshell, is we're looking at real forces. You're going to see movies where you can see the thing actually move. George is doing a replication for us, and his problem is going to be not detecting some minuscule force. It's going to be putting about 300 grams onto his very sensitive balance. Okay. Uh, George, I have John Woodland working on reducing the mass of the parts, but at 180 grams for the basic device with the frame and all that, which you see, which I showed in the slides before, that we're not going to mess around with. It's the same as the one that you did 5 years ago. Okay. Anyway, yes, you wish Martin were watching. Martin's not watching. It's okay. We've got replicators lined up. Okay, so we'll know. George's problem is going to be uh, that he needs the thrust balance. The reason why you need the thrust balance is very simple. The chief false positive that's possible in this system is a slipstick action between the device on the linear ball bushings and the stuff, the ball bushings and all that, okay? And the way in which you eliminate that possibility is by running it on a thrust balance that's vibrationally isolated so that the vibration in the device itself does not get to the balance. So the quasi-static forces are the only thing that will cause the thrust balance to be displaced because of the conservation of momentum. Slipstick stuff in the device on the rods and all that will not cause the balance to be displaced from its natural position. Only real forces will do that. That's why the thrust balance is so important. Once we get past that, which will hopefully be sometime fairly soon, you can actually do this without thrust balances at all. You can just put them on, you can put them on a thrust block and measure the motion of the device on the rods, the linear ball bushings on the rods, okay? And you don't need a fancy thrust balance or anything like that. And as I say, when you do the back of the envelope calculation for what Michelle's going to be showing you in a few minutes, we're talking about these things actually producing things at the millinewton level. And as Paul will be happy to tell you, if they're really producing stuff at the millinewton level, the expenditure of power, which I didn't address in those displays, is on the order of a few tenths of a watt or less. Okay. It doesn't take much. The power in these things is almost entirely reactive. Okay. Power dissipation is what actually moves the thing, the force, the work that the forces do and all that. It's a few tenths of a watt, for millinewtons of, that turns out to be newtons per kilowatt in the standard way of addressing the efficiency of these things. So what we're looking at is a system that is competitive with the best electrical thrusters and all that, perhaps better. In principle, this can be taken even farther than that, I expect, and so on. By heavy lift is not unreasonable. that it's being done, to be perfectly frank, with 19 millimeter diameter, 2 millimeter thick discs and a stack of 8 and a little gizmo like this is frankly astonishing to me. I did not expect that we would be able to extract this sort of performance from what was basically a laboratory test device. It was not intended for serious commercial development. Okay, now, that said, a question or two, if there are a question or two, and then it goes to Paul, Chip, and Michelle. Nobody's got a, George, you don't have any questions?
Just wait, just wait.
Just wait.
I had a
Okay,
question, Jim.
Paul. Okay, Paul, it's all yours.
Oh, wait, I think Lance has a question for you, Jim.
Huh?
Lance has a question for you.
Lance has a question. Go ahead, Lance.
Yeah, a couple of years ago, I think it was 2018 in Estes Park, we saw a suggestion that the time profile of, the thrust versus time could be modeled as a three-body effect, and to rule out, whether this could be just a normal Newtonian effect. Have you guys pursued that line? Have you, ever looked at the time profile of the thrust?
You're Lance, let me answer your question. You're talking about the guy who did this so-called simulation? Yeah,
Well, yes,
let
his
me,
name was, Chomperlink or something.
yeah, something like, yeah. Let me tell you what happened with that back channel. The back channel story on that is that he sent his code to then Heidi, who dissected it and discovered that what he had done was he had engineered his code to get the display that he showed that he wanted. He had a preconceived conclusion and it was built in, baked into it. He had utterly unphysical parameters for this and that and the other thing and so on. And he got the result that he wanted. Okay, three-body solutions still conserve momentum, and three-body solutions cannot produce net thrust, no matter how you sling them around.
Yeah, and I thought it raised a good point, to my mind, is this a way to validate or falsify, i.e. to do a three-body simulation, let's say correctly, and prove that if it was a three-body that you would get a different time signature. I had not thought about the time signature as part of the data until that suggestion. I think it's still a sound suggestion. I wondered if you guys had thought about pursuing it as a way to
No,
buttress.
to be perfectly honest, Lance, the answer is no. It violates momentum conservation. Momentum conservation is a really, really important physical concept. And I hear you that it's an easy way of answering something like that, where you look at it from the computational point of view as an interesting problem because there are no closed form solutions for three bodies, exact solutions. So yes, could you conceivably do something like, yeah, I suppose you could, but you'd still get the same answer in the end, which is no, you can't produce thrusts that way.
Exactly. So when you said it doesn't conserve momentum, were you talking about the experiment or the simulation?
No, I'm talking about the simulation. The simulation itself does not conserve momentum. Okay, it can't. No system of n bodies in an isolated system can produce thrust, is what it boils down to. That's what conservation of momentum says. Okay, actually, conservation of momentum.
And you yourself said that your system doesn't produce steady thrust either.
No, it doesn't produce steady thrust because we have a problem with this system, and Chip's going to talk about this. This system, in order to get the very large thrust, you have to go to a very high Q system. Okay, when you saw that thing progressing and all that, it goes boom, boom, like that. That's a low frequency response to a much sharper spike, and you'll see some of this in the movies that the others are going to show you and all that. Okay, the problem there is the best you can do is a quasi-stationary thrust by sweeping through it slowly enough so that you can see the actual motion and all that, but fast enough so that it doesn't get damped out entirely by the thrust balance, low pass characteristic. Okay. Chip is designing an amplifier that is going to hopefully lock onto and track the high Q signal so that you can choose a single frequency, turn the thing on, it produces thrust in a particular direction, and then it locks onto and tracks the resonance that produces the thrust, and you get steady thrust, okay? But Chip's amplifier, which is suffering from the same sort of thing that all experimental stuff does, namely it's taking longer than anybody imagined. Chip's amplifier is not yet built, but it's on its way. And
Well,
when we get
I
that,
think, yeah, I don't want to send you too far down the rabbit hole. I know there's other people waiting and you have a schedule to keep, but thanks for allowing me to raise that issue.
no, that's perfectly okay, Lance. We're not trying to sell anybody a pig in a poke. You get to see the movies, you get to folks fix at it and all the rest of that. But
Yeah.
wait till you see these things actually move. That's really, frankly, when we first saw them, Hal and I first saw these things, when it's on a really good resonance and all that, literally it jolts the thing and you see it physically move somewhere between a half a millimeter and a millimeter as it sweeps past that resonance. Okay, so
Jim,
yes.
Jim, can
Yes,
I, George, the trace you showed, the red trace had a dip and then a peak and then a
Yes.
dip and then
The outgoing
well,
part of, yeah,
and can you explain why, as you're going down in frequency,
sweeping down,
you have a dip rather than a peak?
it depends upon the phase of the second harmonic with respect to the fundamental, George.
Okay.
Sometimes when everything's a little bit different, you get ones that go up and then down, and then the tail of that is what you're looking at. If you look at the second harmonic in the FFT display, is what you're seeing is an actual mechanical exponential decay of something that's been forced as first one and then the other direction, and then it tails off. That's the reason why I showed you that one. It's really simple. Paul and Chip and Michelle are going to show you stuff that's much more complicated, okay? And I don't want you to get lost in the forest because of the trees, which is why I showed you that simple one.
Okay, thanks.
Hey, Jim.
Yes, let them go ahead and do their thing. Okay, they've got a half an hour to do their thing. Okay, that
Who's next?
I've taken up more than enough time.
Jim, who's next?
Paul,
I'll take it if you want me to.
Go ahead,
yeah,
Paul.
go ahead.
Okay, I'm going to share screen. And there, no. There I am right there. Okay, this is the run that Jim and Heidi were all excited about. And again, this is this is the power on, this is the power off. This is the response frequency, no, the amplitude displacement response of the torque pendulum when it's going through 40 kilohertz. In this case, again, it's an impulsive force because you're drifting through. Okay, I'm going to need to back up. The thing that Jose Rodel pointed out to everybody repeatedly is that the thing that you have to optimize in these stacks and these PZT mega drive systems is quality factor. You've got to maximize the quality factor, i.e. minimize all of the frictional losses in the system to obtain any kind of decent thrust production. That's what the ball bearings have done for the system. They have removed almost all of the mounting friction that was in the previous mounting system with the L bracket and the rubber visco damping rod, and your displacement should just come from springs, very high quality springs, either the arch variety or the coil variety. And that's what this current system right here is doing. The first resonance that we come to is about a 40 kilohertz resonance. And you get this large spike. It's about 18 micronewtons that is pre-filtered, as Jim mentioned, the low pass filtering of the torque pendulum. It's a passband filter of about 6 hertz. And you're doing a 1 kilohertz per second frequency sweep. You only go through the active thrust generation portion of it for maybe about half a second at most. And so you are only seeing an impulsive reaction from the PZT stack on the system. And it is based on those two elements, the bandwidth of the quality factor derived bandwidth of the entire mega drive electromechanical system. And we're guessing right now, I made it wag an estimate somewhere between a overall electromechanical quality factor of between 100 and 1,000 now. And that's why we're getting such strong responses with power inputs that are much less than a watt, more on the order, and I say power, that's a dissipated power being converted into heat in the stack and the bearings and everything else. But since the quality factor is much improved over our previous attempts, this is why we're starting to see what we think when we have an actual, an answer to George. As Jim said, I need to go to my next slide. Hang on. Where is it? Damn it, where are you? There. Sorry, guys. All right, no, there. Okay. Now, I did the same plot that I just showed you. I dialed it back to five seconds into the run, so it's right at 40 kilohertz. There's the fundamental at 40. There's the second harmonic at 80 kilohertz. Now, the main thrust is generated on either side of the resonant peak between the fundamental at 40 and the second harmonic and fourth harmonic, etc. And it's very phase dependent on what side of the harmonic, the resonance that you are on. Above it, it'll produce negative thrust. Below it, it should produce positive thrust depending on your units. So the problem with doing a frequency sweep is that you not only, and I just thought of this, you not only are you're generating a positive thrust pulse and then a negative thrust pulse just as you go through the resonant peak. So I agree with Jim. We're probably producing hundreds, if not thousands, of micronewtons now. And please note, the thrust will be proportional to the second harmonic amplitude relative to the first, the fundamental. It's currently down about 26 dB. And Jim is relying strictly on the SM111 and the other materials, self-harmonic generation. We're not injecting these signals. They're being self-generated because of the electromechanical interaction of the stack and the amplifier. So that, and over here, as you'll see, my best guesstimate of the input power for this particular data run was about 100 milliwatts, or a tenth of a watt, which equates out to about, that's a 0.1 Newton per kilowatt if you just take the native 18 millinewtons that I mentioned before. But if you take all the pre-filtering and the bandwidth the limitations of excitation on the resonance and the plus minus swing that's actually happening, we're probably generating something on the order of 500 to 1,000 micronewtons. And that's about all I have got. Oh, that's it. I think it's off to Michelle now. Michelle?
Well, I'm here. Hi, everybody. Thanks for your presentation, Paul. You covered a lot of stuff I was going to, so I'm going to make mine a little shorter. So let's see, I need to share my screen.
Well, you could just say what I said again and just reinforce it.
I'll do that right now. And okay,
There it is.
Bingo.
well, this picture was taken from 2016. I think everybody who was there remembers that.
Oh, yes.
It's very nice.
The
Where we
gods are
started,
speaking to us.
yeah, where we started was this summer when I got involved was the same thing that everybody been showing you, and aluminum mass, brass mass, L-shaped bracket, PCT stack. I thought there had some limitations onto it, so it led us to, after some really good Zoom meetings, to say we will couple right to the center of mass of the device. We simply go to a null point in the vibration. And what this did is made a device very symmetrical in operation to look for an asymmetrical effect. So we built this, which is, Jim has showed this to you, with the brass mass, aluminum mass, PZT. And also Hal has showed you why we did the center of mass beam deflection back and forth with the weight, so we could get an idea how much, if the device was going to be set on the stainless steel rods, how much we would deviate this, the torsion pendulum. And that worked out to about 0.5 millimeters, or about 8.33 micrometers. Let's see. We came up with doing a centering springs because we didn't want to load anything up with friction. So we did 8,000 centering springs made out of guitar strings, looped them around, which is very kind of hard to do. So that allowed a centering action of the device on the stainless steel rods. And there was some research that was done on this. Jose came up with saying that because of the friction, coefficient of friction and stiction of the linear springs, they shouldn't move until we hit at least 412 micronewtons. Well, we were already moving, so that led us to do some extensive work into finding out why they did move. And what we did find out is that in MEMS, with cantilever beams and stuff, one of the ways to get them unstuck is to use vibration. So that's exactly what we were doing, is the vibration of the stack was allowing the linear bearings to float on the rods, virtually friction-free. So we ended up with basically a assembled area like this, with a large mass on one end to stabilize the rods. And this is what we have currently. And I know everybody's expecting some videos here, so I'll get to it, but this is what the current setup is. One of the things that I found interesting is that we were taking videos of the device operating, and nobody had done that before. And if you take a video of that device, a high resolution video, you can set and process that video and get motion enhancement of that video. And this was done by researchers at MIT CSAIL and Quanta Research Institute. And their company is called Lambda View. So I think I'll get right on to some video here. This is a video that we did, one of the very first videos that we did, and I'll repeat this. The device is operating, we're doing a 40-time enhancement of motion. You can actually literally see the springs vibrating.
You can see the
This is through the
springs.
frequency sweep. of 45 to 25 kilohertz. You can literally see the springs vibrating in this image
Yes, that's,
at a 40 times enhancement. The device
Yeah.
goes through resonant and you can see it move.
the whole thing is moving now.
The whole thing is moving.
Yeah, rather violently.
Well, it's 40 time enhancement.
Well, I know.
Yeah. So
One of the other things you need to point out, Michelle, is that these double loops are they're just on one ear in this particular instantiation. So that makes the test article pitch up when it's.
yeah, it does pivot a little bit. And that's one of the things that came out in these videos
Mm-hmm.
was that we were asymmetrically connecting to the device and it was pivoting a little bit.
Right. You need to load each ear equally.
Correct. Okay. Now,
You just
we'll
bailed
share
out.
screen again without the springs. Took the springs off, reset it up. Sorry for the noise. Okay, we took the springs off and did another run later the afternoon. So the device is just floating in. It's not centered into the device or in the brackets at all.
There you go. Now it's going to get slung around.
So if we didn't have the springs, it's kind of like how it would end up doing.
Mm-hmm. And remember, that's 125 gram system, so that's what's getting slung around.
Yes. So that allowed us to go to the,
Sorry, Michelle, it's George here. Could you repeat that video?
oh, sure. Let me back up.
Thank you.
There we go. Can you see it?
It's
Yes.
going now.
Why don't you start over, Michelle, one more time? Thank you.
Oh, you're welcome.
.78, bang, 1 millimeter. There's 4 millimeters. Back. And each time you go through a thrust reversal, it's going to reverse the direction of travel.
George, did you get to see that?
Yes, thank you.
Okay.
George, you're going to get one of these devices, maybe two, so you'll be able to do all this for yourself.
Now, what we did do is we turned around. This is with a 40 time enhancement. To observe everything on the video. And this includes bracket, this includes device. Is everybody seeing this?
I'm also looking at the side bands on the harmonics that are fascinating.
Yeah. But with this enhancement, and this is going from 0.1 hertz all the way up to 15 hertz. What you're seeing is the response curves of the torsion arm. You're seeing the device move the actual torsion arm back and forth. You can see as it accelerates and moves the torsion arm.
Mm-hmm.
This is kind of like having a laser vibrometer in your eyes. So we can evaluate the movements of the device, how it accelerates, how it compares to the spectrum analyzer, how it compares to the voltages, how it compares to the temperatures.
So
It's
in this
been a
kind of a
great-
case, in this case then, what's the point of having this on a thrust balance if you can just measure the displacement while it's on the sledge?
That exactly. That
And
is something
also-
that is something we are looking at.
Yeah, and also, what kind of temperature does the device get to during a run like this? And given the
That's-
close tolerances of those rods inside the linear ball bearings, is there any thermal effects that you're going to get with as these components heat up to maybe increase the friction?
For a 20-second run, Greg, it's typically about 5 to 10 degrees centigrade rise.
That's not too much.
And that's in the PZT stack itself. It takes a while for all that thermal, because of the PZT has such a lousy thermal conductor, 1 watt per meter Kelvin or less. It takes quite a while for it to percolate into the brass and the aluminum.
And how are you getting that number?
The temperature rise,
Yes.
thermistor on the aluminum end cap of the PZT stack.
It's the green
Actually-
trace at the bottom of the strip chart recording, Greg.
Green
That's
trace.
Heidi has it set up so that it doesn't display the trace until after the run's over.
Oh, I see.
Yeah, I cut the video off because of the processing time here, but Paul is correct. It only rises about 5C.
It's George here. Can I ask a
Thank
question?
you.
I thought Paul said that when the second harmonic reached a larger proportion of the fundamental, you get the largest thrust. If you repeat that slowly and stop it, the second harmonic seems to stay fairly constant and actually goes down when that large thrust signal occurs.
George, you're dealing with multiple filtering elements that are skewing the time base.
The other thing, George, is that the thrust is a lagging indicator of what's going on in the FFT. So you
Okay.
get a large second harmonic and it looks like it happens just before what you see in the thrust trace.
Okay.
Now
So
on
have you-
this, go ahead. I'm sorry.
One more quick question. Have you actually measured, well, has anybody measured in some way before before the device is active? Have you measured how much resistance is being offered by those wires that are all hanging there running into the device?
There is some tension involved with those cables that probably need to be improved, Greg. Probably
right.
they do.
Absolutely correct, Greg. We have tried to end up doing loops on those wires so that the impact on the device would be minimal.
Yeah.
The wires, Greg, are soldered onto the electrode tabs close to the aluminum cap so that they don't interfere with the rest of the hardware as much as possible.
Mm-hmm.
So this event here at 0.1 or a tenth of a volt works. It pegged our system at about 100.
About 120.
Yeah, somewhere around 120 micronewtons.
Oh, that's
Yeah.
right. The voltage
Yeah.
scale on the right side and the upper left picoscope trace is 12 volts, and that's
Yeah.
where it's flat tops because of the power supply limitations on the instrumentation.
It's being clipped by the amplifier and the position sensor,
Mm-hmm.
which has
Mhm.
plus or minus 12 volt supplies.
We didn't expect to run into this, but
No.
we did.
We're so sorry.
Yeah. So I'm going to go to, now we debated on whether to show this one or not, but this is with the springs,
The helical springs.
the helical springs, yes.
Mhm.
And, but it showed such a wonderful trace because of all the video processing work that we did prior to this. It showed us that we needed to go to a helical spring to capture all the ears on the device so that we could make it more uniform as far as transmitting its thrust event into the torque pendulum. We have new springs on order. This is a 0.1 hertz to 15 hertz video enhanced movement. The chaff you see on your wait a minute here. Are we sharing?
Yes.
Yeah.
Okay. I'll stop it and pause it here. Here's the new springs. Since this was just done, we didn't have an opportunity to get
The right ones.
the right ones. So from a McMaster car, we got the best we could. And the tension on these springs are 100 times the wire springs that we used.
Right. The gold-plated piano wire. as
I
Jim
know.
likes to
So,
know.
so there shouldn't be really any movement at all because it constrains that device pretty well. We do have new springs ordered, a little bit softer touch.
The
I
right
don't,
ID.
yeah, and they will allow us to set them in here so that there's no touching of anything. So, but I wanted to show you the dirt so you could see the sky. So here we go. Now this is the one that showed the two thrust events. The one was the Mach effect taking effect, and the other one was the mechanical.
Right, 40 kilohertz and down at around 30 kilohertz.
30 kilohertz, right.
Mm-hmm.
You can.
And
Now,
the wires, go ahead, I'm sorry.
the interesting thing about this is there's absolutely very little movement of the device itself.
Right.
Here, can you see this again? Now I'll play this one again. Back this up. Here's our first thrust event right here.
Mm-hmm. Now, Mr. Sell, in this particular view, upper right corner where you have the video, is that image, is that motion enhanced or not?
No, it is not.
Okay, that's why I'm not seeing much. Okay.
No,
thank
you will not see much here. Well, the spring, you might not see much at all because the springs are like 100 times of what they should be.
you. Exactly.
But the interesting thing is you still deviate the torsion pendulum.
Mm-hmm. And there's almost no center of mass movement at all.
No.
Yeah. The force effectively is acting directly on the balance.
And the interesting thing is the balance does not respond that well. If you take a look at here at the ring down effect, this is the natural resonant frequency of the torsion arm
You can tell the six hertz ring down.
right
It's
here.
real obvious.
Yes. This definitely is not. You can see the thrust event going up, thrust event being driven down and back. And that thrust event is way different than the natural resonant frequency of the system.
Yeah, right. Okay.
So who's next?
Chip,
Chip. Good.
you're off, Shell. Take a deep sigh.
Yeah. Thank you, everybody.